To stand beneath the sky and wonder what lies beyond it is one of humanity's oldest impulses. Even before we had words for planets or stars, we felt the pull of the unknown stretching above us like an ancient invitation. Today that question has transformed into something far more precise and far more haunting. Will humanity ever escape the solar system, or are we destined to remain forever in the shadow of our own sun? The question lingers like an echo across centuries of curiosity, reminding us that the cosmos is not just a place we observe but a boundary we ache to cross. Imagine the sun rising over Earth not as a comforting beacon of life but as a vast gravitational monarch holding everything in place with silent authority. Its light spills across oceans, forests, and concrete cities, yet beneath that warmth lies a power so immense that every spacecraft we have ever launched has struggled to break free from it. In this moment, picture humanity standing on a small blue island adrift in a cosmic sea, staring outward with equal parts hope and fear. The solar system stretches far beyond what our eyes can see, a realm filled with swirling storms on Jupiter, icy plains on Pluto, and the quiet darkness that waits beyond Neptune. And somewhere in that vastness the question grows even louder: can we ever leave? Our rockets today still tremble against the sky like primitive arrows. When they roar upward, fire and smoke trailing behind, it feels as though we are watching the first timid attempts of a species learning to crawl beyond its cradle. But no matter how high they climb, the immensity of space always presses back. The speed required to escape the sun's grip is staggering, a figure that turns ambition into something bordering on madness. And yet, despite the overwhelming odds, we continue to dream, because that dream is stitched into the fabric of what it means to be human. Consider the generations that have looked upward before us. Sailors navigating by starlight, astronomers charting planetary paths with trembling hands, children whispering stories of faraway worlds. They all carried a spark that refused to be extinguished. That same spark burns in us now as we stand at the edge of an era where interstellar travel feels both impossibly distant and achingly close. Every photograph from a distant probe, every shimmering telescope image of a nebula, every discovery of an exoplanet reminds us that the universe is not empty. It is overflowing with possibility, and we have barely taken our first breath of it. Yet with every dream comes a shadow. What if the solar system is not merely our birthplace but our prison? What if no matter how much technology advances, the distances remain too vast, the energy demands too merciless, the physics too unforgiving? Such thoughts creep in like a cold wind, whispering that we may be cosmic spectators rather than explorers. But even as fear settles in, a counterforce rises, an instinct older than civilization itself. We are a species built to push against boundaries, to walk toward the horizon even when we cannot see the land beyond it. Imagine standing on a quiet beach at night. The waves roll in, the sky above glittering with a million unreachable points of light. For a moment, you feel impossibly small, a single heartbeat in a universe that has existed for billions of years. But then something shifts. The smallness becomes a kind of freedom, a reminder that we are not confined by what we are now but by what we have yet to become. Our limitations are temporary. Our desire to transcend them is not. This is where the true weight of the question settles in. Escaping the solar system is not only a scientific challenge, it is an existential one. It asks us who we are when faced with the unknown. Are we creatures of caution, content to remain within the boundaries that nature has drawn? Or are we wanderers destined to follow the faint trails carved by light itself into the darkness? The answer may define not just our future, but the entire arc of our story as a species. And as we look forward, the mystery deepens. Perhaps one day our descendants will stand on a vessel drifting between stars, watching the sun shrink behind them until it becomes just another distant point in a sky filled with countless others. Or perhaps the answer is far stranger, involving technologies or life forms we can barely imagine today. The uncertainty is both terrifying and intoxicating. For now, the question remains suspended above us like a star we cannot reach. Will humanity ever escape the solar system? The story has not yet been written, but its opening lines have already begun to form. They whisper of struggle, ambition, longing, and the timeless pull of the unknown. They remind us that every great journey begins long before the first step is taken, in the quiet moment when we dare to ask what lies beyond the world we know. And somewhere in that quiet moment of questioning, a new spark begins to form, one that feels like both a memory and a prophecy. It suggests that the answer may not come from the machines we build, but from the courage that drives us to build them. That spark keeps growing still today. Beneath the calm glow of the sun, an invisible prison surrounds us. It is not made of iron or stone but of gravity, radiation, and orbital mechanics. forces so immense that they shape the destiny of every planet, moon and fragment of dust within the solar system. To stand on Earth and look upward feels liberating, yet that very sky masks a cage far more powerful than any wall humans have ever built. Gravity holds us in place with a grip forged in the heart of the sun itself, anchoring our world to an orbit tens of millions of kilometers wide, and this silent pull is the first reminder that freedom beyond the solar system demands far more than desire. Picture Earth as a marble suspended on a cosmic string, forever circling a blazing star that refuses to release it. Every spacecraft humanity has launched must claw its way out of this gravitational well, expending enormous energy just to reach the emptiness of space. Even then, they remain tethered to the sun's immense pull, caught in its invisible web that stretches far beyond Pluto. The deeper we look into the mechanics governing our cosmic neighborhood, the more we realize that the solar system is not simply vast. It is structured in a way that prevents easy escape. Its massive planets, powerful magnetic fields, and streams of solar radiation form walls that shift and bend, but never truly open. Imagine these gravitational forces as colossal, unseen chains wrapping around our planet. Earth's orbit around the sun may feel serene and predictable, but it is also a reminder that our world is trapped in a perpetual dance it cannot leave without extraordinary effort. The same gravitational embrace that provides stability becomes an anchor when we dream of venturing farther. Venus, Mars, the gas giants, each planet moves within its own carefully carved path, held firmly in place by equations that dictate their fates with mathematical precision. The solar system behaves like a finely tuned clockwork, majestic yet confining, trapping everything within a series of nested orbits. Now consider radiation. Streams of charged particles erupt from the sun every second, racing outward at incredible speeds. These solar winds create a vast bubble around our system called the heliosphere, a protective yet confining boundary. Within it, radiation flows like a turbulent ocean. Outside it, cosmic rays drift in from distant galaxies, threatening life with their deadly intensity. It is a barrier that both shelters and endangers us, a paradoxical veil of energy shaping the limits of where humans can safely travel. To escape the solar system is not just about breaking gravitational bonds, it is about surviving in an environment that grows increasingly hostile the farther we move from the sun's influence. As we envision spacecraft moving through this cosmic landscape, the challenge becomes clearer. Instead of navigating open space, they must weave through gravitational tides, radiation storms, and the pull of planets that can either help or hinder their path. A tiny miscalculation can trap a spacecraft in orbit around a planet, fling it off course, or send it spiraling into the sun itself. The solar system is a maze with shifting walls, beautiful, intricate, and unforgiving. Every route outward is fraught with obstacles carved into space by forces we cannot negotiate with, only endure. Think of the sun as a cosmic monarch reigning over a vast empire. Its gravitational authority extends billions of kilometers in every direction, binding planets, comets, asteroids, and dust into orderly yet restrictive motion. Even the fastest human-made object, the Parker Solar Probe, remains under the sun's control despite its extreme speed. The notion of escape begins to feel almost rebellious, like a revolt against the natural order of the cosmos. For all our achievements, humanity remains a species trying to break free from a system designed to keep everything in place. The deeper we explore these forces, the more we recognize how deceptive the night sky truly is. Those specks of light we see, stars, planets, galaxies, suggest openness and freedom, yet our place is locked within a structure of breathtaking rigidity. We inhabit a cosmic fortress whose walls are made not of matter, but of fundamental laws. They cannot be broken. They can only be worked around, exploited, or endured with unimaginable amounts of energy. The solar system is both cradle and cage, nurturing enough to allow life, restrictive enough to challenge its evolution beyond. As the realization settles, a subtle tension builds. This is not merely a scientific limitation, it is an existential one. Are we a species meant to orbit our star forever, constrained by the very forces that created us? Or does our yearning to escape hint at a deeper truth, suggesting that the cage is not absolute but simply the first test in a longer cosmic journey? These questions linger like shadows at the edge of the solar system, stirring both fear and wonder. And as we contemplate them, one truth becomes clear. Understanding the solar cage is the first step toward escaping it. Because before we can break free of invisible walls, we must learn to see them. And the moment we truly see them, the mystery deepens. What lies beyond those walls and what price must we pay to reach it? They were fragile machines by today's standards, thin metal shells wrapped around fuel tanks, bolts trembling, electronics flickering like uncertain hearts. Yet when humanity first pointed these early rockets toward the heavens, something extraordinary happened. For the first time, our species dared to challenge the sky not with myths or dreams, but with fire. The moment those engines ignited, their thunder rolling across deserts and forests, it was as if humanity had thrown its first stone at the cosmic barrier that had overshadowed us for millennia. These primitive rockets, roaring upward against gravity's crushing pull, marked the beginning of a struggle that still defines us, the attempt to liberate ourselves from the solar system's grip. Imagine the world in the mid-20th century, when the idea of reaching space felt like trying to leap over a mountain. Scientists scribbled equations late into the night, imagining engines powerful enough to pierce the sky. Engineers assembled rockets in silent hangars, their hands guided by a strange mix of fear and hope. And when those early test flights began, each one carried more than metal and fuel, it carried the weight of thousands of years of imagination. When the first rocket shattered on the launch pad, flames curling upward, it was not just a machine breaking. It was a reminder of how unprepared humanity truly was for the vastness beyond. Yet the failures only intensified the desire to try again. Each explosion felt like a challenge thrown back at us by the universe itself, as if the cosmos were testing whether we deserved to reach it. And every time a rocket rose, even for a few seconds, it cracked open a door that had been sealed since the birth of the solar system. The emotional contrast was overwhelming, triumph followed by disaster, hope followed by fear. Engineers who celebrated a successful launch one day might find themselves picking through twisted metal the next. The path forward was never straight. It was carved through persistence, sacrifice, and a willingness to push against the impossible. When Sputnik finally broke free of Earth's atmosphere in 1957, it was more than a sphere of polished metal orbiting above us. It was a declaration. Humanity had launched its voice into the night, a steady radio pulse that echoed across continents. People stood in fields and city streets, staring upward with a mixture of awe and dread. If a small machine could circle Earth, what else might follow? Some felt exhilaration, sensing the dawn of a new era. Others felt vulnerability, fearing what the sky now held. Sputnik was a whisper from the future, hinting that the cage of Earth was not unbreakable after all. A few years later, when Yuri Gagarin became the first human to orbit the planet, the moment transcended science. As he looked down upon Earth, a shimmering blue sphere wrapped in delicate clouds, he saw the world in a way no human had ever seen it. Borders vanished, continents blurred, and the fragility of our existence became unmistakably clear. Gagarin's heartbeat became humanity's heartbeat. His survival was our survival. His courage was a mirror reflecting our deepest longing to explore the unknown. Yet even as he completed his orbit, the truth was unavoidable. He had escaped Earth but not the Sun. He remained bound to the same cosmic leash that held all of us. The Apollo missions intensified the struggle, transforming rockets into symbols of ambition unlike anything before. The Saturn V rose from its launch pad like an engineered titan, its engines producing a force so immense that the ground trembled for miles. People watched with breathless anticipation as astronauts ascended toward the moon, their spacecraft glowing like a tiny beacon against the dark backdrop of space. For the first time, humans had reached another world. They left footprints in dust untouched for billions of years, planted flags that fluttered in a windless silence, and returned with stories that rewired humanity's sense of possibility. Yet even this triumph carried its own shadow. The moon, despite its distance, remains firmly within the sun's grasp. It was a step outward, not a step away. The solar cage still surrounded us, silent and unbroken. The rockets that carried astronauts home were celebrated as marvels, but they were also reminders of how far we still had to go. Every mission revealed new hurdles, fuel limitations, navigation challenges, human fragility, and the sheer vastness of the space that awaited beyond the moon's orbit. As space agencies experimented with probes and satellites, they began pushing further, first to Mars, then to Jupiter, Saturn, and eventually beyond the planets themselves. Voyager 1 and Voyager 2 became humanity's most daring attempts to escape the sun's domain, their golden records carrying messages of who we are and what we dream of becoming. The Voyagers drifted through radiation belts, past swirling storms larger than Earth, and into regions where sunlight thins into a faint whisper. These machines were our scouts, venturing into the unknown long before we dared to follow. And when Voyager 1 finally crossed into interstellar space in 2012, it felt like humanity had exhaled after holding its breath for generations. But even this milestone was symbolic. Voyager was free, but we were not. Looking back at these early attempts, it becomes clear that humanity has always walked a knife's edge between brilliance and fragility. Rockets are triumphs of engineering, yet they remain fundamentally primitive compared to what is required for true interstellar travel. They burn enormous amounts of fuel to achieve a few minutes of thrust. They carry delicate humans whose bodies are painfully unprepared for cosmic conditions. And each mission, no matter how successful, only underscores the scale of the challenge ahead. But these first steps, trembling, explosive, courageous, were essential. They taught us that escape is possible but not easy. They revealed the immense strength of the forces holding us in place. They showed us the beauty and terror of the void beyond our planet. And they ignited a question that grows louder with every scientific breakthrough. If these early rockets were our first attempts at freedom, what comes next? The emotional tension lingers in the air even now. We have touched the edge of the solar system with machines made of metal and wires, but we have not yet sent humans beyond the moon since 1972. We stand at the threshold, uncertain whether our species is on the verge of cosmic expansion or destined to remain confined to our celestial home. The memory of those early attempts continues to inspire and challenge us, reminding us that every great escape begins with small, trembling steps, and that the universe is watching to see if we will take the next one. The solar system looks peaceful from a distance, a serene arrangement of planets orbiting a golden star, drifting in quiet harmony. But the moment we zoom out, the illusion dissolves. What appeared manageable becomes overwhelmingly vast, a scale so immense that human intuition collapses under its weight. To escape the solar system, we must first confront the staggering truth of the cosmic distances involved, distances that turn even our fastest spacecraft into slow-moving dust motes drifting through an endless sea. This realization is not comforting. It is humbling, almost frightening, because it reveals just how small and slow we truly are. Imagine standing on Earth and looking up at the sky. The moon feels close, almost reachable, a familiar companion in the darkness. Yet even this closest celestial neighbor is nearly 400,000 kilometers away. A distance so large that if you drove without stopping at highway speeds, it would take months to arrive. And the moon is nothing compared to the rest of the solar system. Mars can range from 56 million kilometers to more than 400 million kilometers from Earth depending on orbit. Jupiter sits hundreds of millions of kilometers farther, its swirling storms like distant bruises on the horizon. The distances grow not linearly but exponentially, stretching outward like a cosmic staircase with steps too large for human legs. Now imagine trying to escape the solar system entirely. To break free from the sun's gravitational pull, you don't just need to travel millions of kilometers, you must reach speeds measured against the sun's binding force, a force that extends far beyond what we can see. The sun's gravitational influence reaches out for more than a light year, shaping comets, icy debris, and dust fields that orbit silently at the edges of the Oort cloud. To outrun that influence isn't just a challenge, it's a battle against the foundational mechanics of the entire solar system. Every spacecraft humanity has launched seems fast to us, yet on a cosmic scale they crawl. The Voyager probes, among the fastest machines ever built, travel at over 17 kilometers per second. At this speed you could circle the Earth in minutes. But even with such incredible velocity, Voyager took more than 35 years just to reach the region where the sun's influence begins to fade. And that's still not true interstellar space, not the free, open void we imagine when we think of escape. It's merely the thin outer skin of the solar system, a place where the sun's power is faint but still present. The true boundary lies far beyond, and crossing it requires not just speed but unimaginable endurance. Envision this journey as a cinematic pullback shot. The camera lifts above Earth, passing the moon, gliding past Mars, drifting beyond the asteroid belt. At each stage, Earth shrinks until it becomes a pale blue speck swallowed by darkness. Soon even the sun begins to shrink into a blinding coin of light. The planets become faint, distant dots, each swallowed by infinite black. Distances grow so large that even light, the universal speed limit, takes hours to crawl from the sun to the outer planets. And somewhere out there, wrapped in this cold immensity, lies the question: how could a fragile species like us ever hope to outrun such distances? This is not merely a matter of travel time. It is a collision between human ambition and the incomprehensible scale of space itself. The contrast is almost painful. Our rockets burn for minutes, but interstellar journeys require propulsion that lasts for decades or centuries. Our spacecraft weigh tons, yet interstellar escape demands systems so efficient they could glide through space without constant fuel. The mismatch feels like a riddle designed by the universe, a challenge that tests not just engineering but imagination. Consider the void between planets. It is not empty but filled with particles, radiation, dust, and drifting debris. These fragments can be deadly at high speeds, turning tiny grains into projectiles capable of tearing through metal. As distance increases, communication becomes delayed, then impossible. Navigation becomes a guessing game woven with mathematical predictions. With each kilometer gained, the certainty of control weakens. We designed spacecraft to operate within the protective reach of Earth, yet the journey outward pushes them into realms where no human hand can intervene. And beyond all this lies the greatest challenge: energy. The farther we want to go, the more energy we need. But fuel adds mass. Mass slows acceleration. Slower acceleration demands more time. More time increases exposure to radiation and cosmic hazards. It becomes a cycle that traps spacecraft within the limits of current technology, a cycle that feels intentionally cruel, like the solar system mocking our attempts to leave. The emotional impact of this scale problem is profound. It transforms optimism into tension, hope into humility. Yet within that tension lies a strange kind of beauty. The universe becomes a mirror reflecting our limitations, but also our courage. The very fact that the solar system is so huge makes the dream of escaping it feel heroic. Each challenge becomes a cinematic obstacle, each distance a reminder of how far ambition can stretch. As we stand on Earth today, staring into the night sky, the distances seem silent and indifferent. But they are not impossible. They are warnings, tests, thresholds that demand innovation beyond what we have achieved so far. Humanity's story is filled with impossible distances we eventually bridged. Oceans, mountains, deserts, skies. The cosmic scale problem is the largest of them all, a reminder that the solar system is not just big, it is overwhelming by design. And as we confront this immensity, a new mystery begins to form. If distances within our own solar system are already this vast, then what lies beyond, in the deeper darkness between the stars? What secrets wait in the spaces too large for imagination and too distant for current technology? The question lingers, unsettling yet irresistible, pushing us forward even as the scale threatens to hold us back. The laws of physics are not merely rules written into textbooks. They are the invisible architecture of the universe, the quiet but relentless forces that decide what is possible and what is forbidden. And when it comes to leaving the solar system, those laws become towering obstacles. They shape every launch, dictate every trajectory, and ultimately determine whether humanity will ever achieve true cosmic escape. To understand our future among the stars, we must walk into the realm of these laws, where mathematics becomes mythic and energy becomes destiny. Escaping the solar system is not simply a voyage. It is a battle against the fundamental structure of reality itself. Escape velocity is the first great hurdle. It sounds like a simple concept, the speed required to break free from a gravitational body. But the sun's escape velocity is not a mere number. It is a wall built out of the star's immense mass. To escape Earth, a spacecraft needs to reach about 11 kilometers per second. But to escape the sun from Earth's distance requires nearly triple that speed, about 42 kilometers per second. Even our most powerful rockets strain to achieve a fraction of that. Imagine running up a hill that grows steeper with every step you take. That is what escaping the solar system feels like. A perpetual increase in resistance, a reminder that the sun's gravitational embrace is far stronger than anything humanity has ever built. Picture a spacecraft at launch. It rises on pillars of flame, engines roaring like caged beasts trying to claw their way into the sky. Beneath the fire and smoke lies a brutal truth. Nearly all the rocket's fuel is consumed in the first few minutes just to break free of Earth's immediate pull. The rest of the journey depends on precision, momentum, and the ability to conserve every ounce of energy. Physics becomes a kind of cosmic chess match, with each maneuver carefully calculated to steal tiny gains from an unforgiving landscape of forces. Even once a craft leaves Earth, it remains far from free. The sun pulls it constantly, bending its path inward unless it carries enough velocity to resist the star's influence. Propulsion then becomes the second great challenge. Chemical rockets brought us to the moon, but they are fundamentally primitive, explosive fuel chambers that burn violently for short bursts before falling silent. They can whisper against the cosmic darkness, but they cannot shout loudly enough to carry humans into interstellar space. Every kilogram of fuel adds weight. Every added gram slows acceleration. And every increase in speed demands exponentially more energy. It is a cruel equation. The harder we push, the heavier we become. The heavier we become, the more impossible escape becomes. Humanity stands trapped in a loop of its own technological limitations, bound by the physics of mass, energy, and motion. Ion propulsion appears elegant by comparison, like swapping a sledgehammer for a scalpel. These engines push ions out at incredible speeds, creating a gentle but constant thrust that can accelerate a spacecraft for months or years. In the vacuum of space, slow and steady becomes shockingly powerful. Yet even here we confront limitations. Ion engines require vast amounts of electrical power, and the deeper we travel into the solar system, the weaker sunlight becomes. Nuclear reactors could solve this, but they introduce risks that humans have yet to fully confront. The universe demands more of us. It demands machines that can sustain propulsion not for hours, but for decades. Orbital mechanics add another layer of complexity. Spacecraft cannot simply point at a destination and fire their engines. They must navigate a cosmic dance of curves, slingshots, and precise timing. The planets become stepping stones, massive partners in a gravitational ballet. To gain speed, a spacecraft may swing around Jupiter, stealing momentum from the giant planet's orbit. But every maneuver must be perfect. A miscalculation of even a fraction of a degree can result in disaster. A drift into deep space, a fatal plunge toward the sun, or a collision with debris invisible to sensors. The mathematics behind these trajectories are beautiful, almost poetic, yet they reveal just how delicate interplanetary travel truly is. In this cinematic landscape of forces, acceleration becomes a precious commodity. Even the smallest push can change a spacecraft's fate over long distances. But the pushes we need, continuous acceleration, powerful propulsion, extreme velocity, are beyond current human capability. To reach the nearest stars within a human lifetime, a craft would need to travel a significant fraction of light speed. But reaching even 10% of light speed requires energy on a scale that dwarfs global consumption. Humanity would need reactors as powerful as stars or groundbreaking innovations in energy storage and conversion. The challenge is so immense that it redefines the very concept of engineering. As we explore these physical constraints, a strange contrast emerges. The laws of physics are both our enemy and our guide. They hinder us, yet they also offer pathways. Gravity binds us, yet also provides slingshots that accelerate us. Radiation threatens us, yet offers clues about energy sources. The vacuum of space is deadly, yet its emptiness allows momentum to persist forever once achieved. Physics does not simply say no. It says, prove yourself. It demands creativity, perseverance, and a willingness to imagine beyond chemical fuels and conventional engines. Consider what escaping the solar system truly means in physical terms. Reaching a point where the sun's gravitational pull becomes negligible. That boundary lies far beyond Pluto, past the Kuiper Belt, and deep into the Oort cloud, a realm so distant that even light takes hours to travel across. To journey there requires more than speed. It requires survival. Cosmic rays, micrometeoroids, extreme cold, and engineering fatigue all become threats. We are not simply fighting gravity. We are fighting the entire cosmic environment. The emotional weight of these scientific challenges creates a cinematic tension that feels almost mythic. Humanity is like a character standing at the mouth of a vast labyrinth. The walls are invisible, the corridors are infinite, and the exit lies farther away than any hero has ever traveled. Yet the desire to escape remains. It burns with a quiet intensity in every engineer who studies propulsion, in every astronomer who charts distant stars, in every dreamer who looks at the night sky and imagines stepping beyond it. This tension reveals something profound. The path out of the solar system is not blocked by mystery, it is blocked by physics. But physics is not static. We discover new principles. We invent new machines. We redefine what is possible. Escape velocity, propulsion, orbital mechanics, these are not fixed barriers but challenges awaiting innovation. They test our ingenuity, our resilience, and our ability to think beyond our current limitations. And so we stand here, in a moment suspended between present and future. We understand the forces that confine us, and we see the immense energy required to break free. Yet even as physics imposes these boundaries, it whispers hints of what might someday be achievable. Fusion engines, antimatter propulsion, solar sails, gravitational assists. Each idea is a piece of a larger puzzle, and each brings us one step closer to the threshold of cosmic freedom. But the mystery remains. We know the physics. We know the challenges. What we do not know is whether humanity will ever master them. Will we find the propulsion needed to outrun the sun's grip, or will we remain trapped by the same forces that brought us into existence? The universe waits for our answer, silent but patient, its vastness both threatening and alluring. And somewhere in that vastness lies the promise that, with enough knowledge and courage, we may one day break the cosmic chains that bind us. They called it the dream that could rewrite destiny, a power source so dense, so furious, so unfathomably potent that even the stars themselves are fueled by its raw violence. Nuclear propulsion became humanity's boldest idea for escaping the solar system, a promise wrapped in equal parts brilliance and danger. It wasn't simply another technological leap, it was an attempt to borrow the very fire of creation. The moment scientists proposed using nuclear detonations to propel spacecraft, the universe seemed to tilt. This was no longer about building bigger engines, it was about weaponizing starlight to claw our way beyond the sun's grasp. Imagine the early engineers of Project Orion standing in empty deserts, sketching designs for starships that would ride shockwaves from nuclear explosions like cosmic surfers. Each detonation would erupt behind a massive pusher plate, sending the craft forward in brutal, lunging bursts of acceleration. It was a method that defied elegance but radiated raw power, a strategy fit not for delicate spacecraft but for steel Titan ships built to wrestle with the void. The idea was both horrifying and magnificent. In these designs, humanity's path to the stars was forged through controlled destruction. Tiny suns ignited in rapid succession, each one carving a few more kilometers of escape velocity from the universe's fist. The emotional contrast could not have been more intense. On one side lay hope, the possibility of reaching nearby stars within a single human lifetime, a feat chemical rockets could never dream of achieving. Nuclear propulsion offered speeds that bordered on the mythic, promising to shrink the solar system from a prison into a stepping stone. But on the other side lay fear, deep, trembling fear. The same technology that had devastated cities could now become the heartbeat of humanity's greatest journey. It forced the world to confront a painful question. Could the power that ended millions of lives be repurposed as the power that saves us? Even the more refined versions of nuclear propulsion carried this duality. Nuclear thermal rockets heated hydrogen to blistering temperatures, sending it rushing from their engines with a force chemical fuels could not match. Nuclear electric engines offered steady, efficient thrust powered by reactors buzzing with controlled fury. These machines were marvels of engineering, yet they hummed with risk. A leak, a malfunction, or a collision with drifting debris could unleash radiation across the void, turning a hopeful voyage into a catastrophic nightmare. The beauty of nuclear propulsion was inseparable from its peril, like a fragile flame cupped between trembling hands. The shadow of nuclear disaster followed every conversation. No matter how promising the numbers looked, higher exhaust velocity, longer sustained thrust, better mass-to-energy ratios, there was always the ghost of what could go wrong. Critics asked what would happen if a spacecraft exploded in the atmosphere. What if debris from a damaged nuclear rocket fell back to Earth? What if a reactor failed mid-journey, leaving a crew stranded in interplanetary space with a silent, radioactive coffin? These questions crawled beneath the surface of every debate, refusing to be ignored. Yet even with these fears, the temptation was overwhelming. Nuclear propulsion offered humanity something no other method could: a real chance at breaking the sun's grip. Imagine a starship racing through the darkness, each nuclear pulse lighting the void with flashes of blinding white. The ship vibrates as shockwaves ripple through its reinforced structure. The passengers feel the tremors not as fear, but as a heartbeat, proof that they are being hurled toward freedom. The stars ahead seem almost reachable. The sun behind dims ever so slightly. For the first time, escape feels tangible. But then another question creeps in, softer yet sharper than the rest. Can humanity be trusted with this power? Not just technologically but morally. A society still grappling with conflict, greed, and fractured unity may not be ready to wield the fire of stars responsibly. A nuclear-powered interstellar ship requires cooperation on a global scale, shared resources, shared risks, shared vision. It requires a human race capable of choosing exploration over domination. This moral tension becomes a hidden gravity, pulling at the dream and threatening to collapse it. Even so, the idea refuses to die. In laboratories and simulation chambers, researchers continue refining nuclear designs. They test miniature reactors, examine advanced shielding, and model the trajectories of missions that could reach the outer planets in years instead of decades. The ghost of Project Orion still hovers over these efforts, whispering promises of a future where nuclear fire becomes the engine of human destiny. And with each new breakthrough, the boundary between hope and danger blurs a little more. The deeper we explore the promise of nuclear propulsion, the more we realize that its real significance is not just technical, it is symbolic. It represents humanity's willingness to confront power on a scale that mirrors the cosmos itself. It forces us to face our contradictions, our genius and our recklessness, our ambition and our fear, our breathtaking potential for creation and destruction. Nuclear propulsion asks whether our species can evolve not just technologically but ethically. And as we weigh these questions, one final mystery lingers like static in the silence of space. If nuclear power is the key to escaping the solar system, what will it cost us to turn that key? Will the journey transform humanity into something greater, or will it demand sacrifices we are not ready to make? The answer hides somewhere in the blinding flash of a nuclear engine, in the thin line between illumination and annihilation, waiting for the day when we decide whether to ignite it. They are more than ships. They are worlds, sealed, wandering microcivilizations drifting through a darkness so deep it erases the meaning of home. The concept of a generation ship forces humanity to confront a vision both awe-inspiring and unsettling. A vessel so vast that thousands could be born, live entire lives, and die without ever seeing the destination their ancestors chose for them. It is the ultimate gamble, an ark launched into eternity, trusting that the descendants of its passengers will carry the mission forward long after the original crew turns to dust. To imagine such a ship is to imagine humanity willingly stepping into a story where the ending lies centuries or even millennia beyond the reach of anyone alive at launch. Picture the ship's interior: artificial suns glowing overhead, casting soft, warm light across towering agricultural domes. Rows of crops sway gently in recycled air, while distant corridors echo with footsteps and laughter. Life inside feels familiar, almost peaceful, but beneath that calm lies an unsettling truth. A generation ship is a closed ecosystem. Nothing enters. Nothing exits. Every breath must be recycled. Every drop of water must be purified. Every malfunction could cascade into catastrophe. This self-contained world hovers in the void like a fragile bubble, isolated from the universe yet completely dependent on it. The deeper the ship travels, the more alien the cosmos becomes, and the more its inhabitants must rely on systems older than they are. The psychological weight inside such a vessel is heavier than any physical danger. Children born aboard the ship will never know Earth's sky, its oceans, its storms, or its gravity. Their existence becomes a paradox. They inherit a mission they never chose, tasked with preserving traditions and goals that belong to ancestors they never met. Imagine standing before a viewport, staring at nothing but blackness sprinkled with distant stars, knowing those same stars will remain unchanged for your entire lifetime. Time loses its meaning. The concept of a destination becomes an abstract legend whispered by elders. The ship itself becomes the only world you know, the only world you will ever know. This is where the haunting contrast emerges. The dream of reaching another star collides with the fear that humanity might lose itself along the way. Cultures evolve. Languages shift. Beliefs transform. On a generation ship, even the mission might be forgotten if future generations decide it no longer serves their needs. Mutiny doesn't need weapons. It needs only boredom, hopelessness, or the rise of new philosophies that reject the sacrifices of the past. The voyage becomes a psychological battleground, where identity, purpose, and unity must be actively preserved or risk dissolving into chaos. Imagine a future generation questioning the purpose of the voyage. Why continue toward a distant star whose light takes centuries to reach them? Why maintain ancient systems built by long-dead engineers? Why endure confinement when the vast, silent cosmos outside seems eternal and indifferent? These questions do not weaken the mission, they define it. A generation ship is not simply a machine. It is a narrative, a story passed from parent to child like a sacred torch. If the story dies, the mission dies with it. This fragility creates a tension that pulses through every life aboard the ship. And yet, within this tension lies hope. A generation ship carries humanity's best qualities: curiosity, resilience, cooperation, and the refusal to accept the boundaries imposed by nature. The people aboard become pioneers not just of space but of culture and society itself. They develop new forms of government to manage resources, new educational systems to teach the mission, new rituals to anchor purpose in the face of infinite emptiness. Their lives, though confined, pulse with meaning because they contribute to a future neither they nor their children will see, yet they believe in it anyway. That belief becomes the engine driving the ship as surely as propulsion. The ship itself evolves alongside its inhabitants. Technologies fail and are repaired. Systems age and are replaced. Entire sections may be rebuilt as new ideas emerge. The ship becomes a living organism, a metal and polymer chrysalis containing the potential for a new humanity shaped by isolation and endurance. But with every adaptation, risk grows. A small oversight in maintenance becomes a slow-burning threat. A misinterpretation of the mission becomes a cultural fracture. A debate over leadership becomes a generational rift. The ship drifts through physical darkness, but its true battles occur in the minds of the people aboard. And outside the hull lies the greatest threat of all, the cosmic void. Radiation seeps through even the best shielding. Micrometeoroids strike the ship like invisible bullets. Resources dwindle no matter how carefully they are managed. A generation ship must last longer than any human invention ever has, surviving conditions harsher than anything faced on Earth. The idea of a vessel traveling for centuries without catastrophic failure feels like balancing hope on the edge of a knife. Yet this is the price of escape, the risk that the ark meant to preserve humanity may instead become its tomb. Still, the dream persists. Humanity's desire to reach other stars burns too fiercely to be extinguished by fear. A generation ship, for all its dangers and uncertainties, represents a future where we refuse to be confined by biology or time. It acknowledges the cruel reality that human lifespans are too short for interstellar travel, and it answers that problem with audacity. If one lifetime is not enough, then let many lifetimes carry the torch. The mission becomes a relay race across centuries, with each generation passing the baton forward in the name of survival and discovery. And as we imagine this vast, drifting world, one final question rises like a whisper echoing through every corridor. Will those future generations still believe in the dream that launched their ancestors into the night? Or will the ship, over time, become a floating monument to forgotten purpose, its destination lost to the slow erosion of memory? The answer lies hidden in the quiet beating hearts of the people aboard, hearts that must choose whether to honor the past or rewrite their own fate in the deep, endless dark. Fusion propulsion is the closest humanity has ever come to touching the heart of a star, a way to borrow the furnace of the cosmos and bend it into motion. Unlike nuclear fission, which splits atoms apart, fusion binds them together, releasing torrents of energy in a burst of light and heat. It is the same process that powers the sun, the same fire that has blazed for billions of years. To imagine a spacecraft driven by fusion is to imagine riding a star's heartbeat across the darkness, guided by a glow that echoes the birth of galaxies. It feels mythic, almost sacred, as though humanity is reaching for something it was never meant to hold. Picture a fusion engine igniting for the first time inside the metallic womb of a starship. The chamber glows an electric blue, particles smashing together at temperatures hotter than the core of Jupiter. Magnetic fields twist and roar as they confine the reaction, holding the miniature star in place like a beast straining against its cage. Outside the hull, the void is silent, but inside, the ship pulses with a low, resonant hum, a sound that feels alive. The crew watches readouts flicker with trembling hope, knowing that if the fusion holds steady, the ship could accelerate for months or even years, gathering momentum with a persistence no chemical rocket could ever achieve. Fusion promises something extraordinary: continuous thrust. Instead of burning everything in minutes, a fusion-powered ship keeps pushing gently but relentlessly, until its velocity becomes astonishing. Speeds approaching a significant fraction of light itself become possible. Distances that once required centuries could be crossed in decades. The vast, seemingly unreachable solar system would shrink before humanity's eyes, turning interstellar travel from a fantasy into a distant but achievable goal. But this dream carries a shadow, a reminder that the very process that lights up the universe is also unpredictable, temperamental, and nearly impossible to harness. Containment is the first and greatest challenge. Fusion demands pressures and temperatures so extreme that matter behaves more like lightning than anything solid or liquid. The fuel, often isotopes like deuterium and tritium, must be compressed and heated until the nuclei fuse, releasing energy in a violent burst. But holding that reaction stable, confining it long enough to produce thrust, is something humanity has yet to master on Earth, let alone inside a spaceship drifting through the void. The magnetic fields required must be finely tuned, powerful enough to corral the screaming plasma without collapsing. A small misalignment, a sudden fluctuation, or a cosmic particle strike could unravel the entire reaction in an instant. Imagine a spacecraft depending on such an engine. Every moment becomes a careful negotiation between stability and collapse. Engineers must trust systems that ride the razor's edge between triumph and catastrophe. The passengers live in a world where the glow of their starborn engine symbolizes both salvation and risk. They might sleep beneath the gentle hum of fusion power one night, only to wake to alarms blaring as the engine falters, threatening to trap them in deep space or worse. Fusion is the definition of controlled chaos, beautiful, unpredictable, and merciless. Radiation adds another layer of fear. Fusion reactions release high-energy neutrons that tear through metal and flesh alike. Shielding becomes a critical part of the design, thick walls and magnetic barriers absorbing the relentless bombardment. But no shield is perfect. Over decades of operation, the hull itself begins to fatigue. Microscopic cracks form, molecular bonds weaken, and components degrade. Every atom of the ship pays a price for the engine's incredible power. Traveling through interstellar space with a fusion drive becomes a constant race against time, not just for the mission but for the structural integrity of the world carrying it. And then there is the fuel problem. Fusion requires rare isotopes, the most promising being helium-3, a substance so scarce on Earth that humanity may need to mine it from the moon, or scoop it from the atmospheres of giant planets. Imagine crews diving into the upper layers of Jupiter, harvesting delicate particles from storms larger than Earth itself, knowing a single wrong maneuver could swallow their ship whole. The search for fusion fuel becomes an adventure in its own right, a perilous quest across alien worlds just to gather the ingredients for freedom. Yet despite all these dangers, fusion retains a magnetic allure. Its light symbolizes progress, intelligence, and the audacity to match nature's own power. A fusion engine is not merely a machine. It is a declaration that humanity refuses to accept the limits of biology, technology, or imagination. The glow of fusion feels like a promise, a future unshackled from the slow crawl of chemical rockets, a path forward carved through ingenuity and courage. But beneath the promise lies an unsettling question. What if fusion is beyond us? What if the same force that fuels stars remains permanently out of reach, taunting us with its brilliance while denying us its strength? Humanity stands at a crossroads where ambition clashes with fragility. We know the mathematics. We can imagine the engines. We can build simulations that show the way. Yet the actual controlled fusion reaction, stable and sustained, remains elusive. As the universe watches in silence, the dream of fusion propulsion hangs suspended between hope and uncertainty. It is a doorway into a future where humans glide between planets like wind across water, smooth, powerful, unstoppable. But it is also a challenge whispered by the cosmos, asking whether we are ready to wield the same fire that has burned since the beginning of time. Somewhere in that glow lies the next chapter of our escape. But until we master the star fire within our grasp, fusion remains a shimmering path we can see but cannot yet follow. They called it the most elegant escape plan ever imagined, an idea so delicate, so impossibly graceful, that it felt more like poetry than engineering. Light sails and laser propulsion are humanity's attempt to ride on beams thinner than hope, drifting across the cosmos powered by nothing more than the pressure of light itself. Instead of brute force and roaring engines, these ships would unfurl enormous sails, shimmering like silver wings, and let photons push them outward. It is a method that feels ancient and futuristic at the same time, like harnessing the wind on a cosmic ocean whose tides are made of starlight. Imagine a spacecraft the size of a house, attached to a sail so thin it makes spider silk feel heavy. This sail may stretch for kilometers, reflecting sunlight or laser beams with flawless precision. When sunlight hits it, the sail trembles gently, barely perceptible motion at first. But in the frictionless void, that tiny nudge becomes everything. A slow, continuous acceleration begins, invisible yet unstoppable. Hours pass, days pass, weeks pass, and the ship goes faster, faster still. With each photon, each tiny push, momentum grows until the craft reaches speeds no chemical rocket could ever hope to achieve. It becomes a drifting shard of silver racing through silence, propelled by the faintest whisper of light. But the true power of light sails comes not from the sun, it comes from lasers. Earth-based or orbital lasers could concentrate immense energy onto these delicate sails, pushing them with far more force than sunlight ever could. In theory, a laser array could accelerate a sail to a significant fraction of light speed, fast enough to reach neighboring stars within decades rather than centuries. The dream becomes breathtaking, a human-made vessel leaving the solar system at velocities that blur the boundary between motion and miracle, a streak of light racing toward the unknown. Yet this dream carries its own strange fear. Light sails are fragile, terrifyingly fragile. A single tear, a small puncture, a misalignment of even a fraction of a degree could destabilize the entire structure. Imagine standing on a ship that is being pushed by a laser powerful enough to vaporize metal. If the sail tilts too far, even slightly, it could be shredded instantly. A mission that took decades of planning could end in a flash of vaporized material drifting like ash in the void. The very force that propels the ship is also the force that could annihilate it. Picture the unfolding of such a sail in space. The panels extend slowly, trembling with tension, glinting like liquid silver against a black backdrop. The sun catches them in waves, illuminating their surface with ethereal radiance. But beneath this beauty lies a constant pressure, a need for absolute precision. Navigation becomes an art form. Tiny adjustments must be made continually to keep the sail aligned with the beam. The ship becomes a dancer balancing on a blade of light, gliding across the cosmos with every motion choreographed to perfection. And behind this delicate performance lies a secret challenge: communication. A craft moving at such extraordinary speed cannot rely on slow, outdated methods. The farther it races, the longer signals take to return, eventually stretching into hours or days. A laser sailship becomes increasingly alone, its fate decided by the accuracy of the initial launch and the fragility of its sail. The crew, if there is one, must rely on autonomous systems capable of making decisions in environments far beyond human reach. Every spark of static, every micrometeoroid impact, every fluctuation in the laser beam becomes a threat. Then there is the cosmic dust. At high speeds, even a dust grain smaller than a grain of sand becomes a deadly projectile. Colliding with interstellar particles at a fraction of light speed could tear through the hull, shred the sail, or cripple propulsion. The ship races through darkness filled with invisible bullets, each collision a potential end to the dream of escape. To survive, the vessel might need electromagnetic shields, dust deflectors, or sacrificial layers, solutions that add weight, and weight slows everything down. The tension between safety and speed becomes a delicate negotiation with no perfect answer. Yet despite all these dangers, the vision of light sails remains mesmerizing. It is one of the few propulsion methods that doesn't demand impossible fuel loads or monstrous engines. It uses the universe's own energy, light itself, to escape the sun's grasp. It represents a new era of exploration defined not by brute force, but by elegance. The sight of a cosmic sail drifting outward would be unlike anything humanity has ever seen, a glowing shard disappearing into darkness, pushed by nothing more than the quiet pressure of starlight. The emotional power of this technology lies in its contrast. It is fragile yet unstoppable, delicate yet immensely powerful. Its propulsion method is ancient, the same force that pushes leaves in the wind, yet applied on a scale so immense it rivals science fiction. It evokes the earliest explorers who crossed oceans with cloth sails, trusting the wind, the waves, and their own courage. Only now the ocean is the cosmos, the wind is light, and the destination is the edge of everything we know. And in the quiet glow of these sails, an unsettling thought emerges. What if this is the method alien civilizations have already used? What if the stars are filled with long-gone sails drifting like abandoned lanterns, remnants of old dreams or lost travelers? The possibility turns the cosmos into a graveyard of ancient journeys, or a map pointing to civilizations far older and wiser than ours. Light sails offer humanity a way to escape the solar system with grace instead of violence. But they also force us to confront the fragility of our existence, the razor-thin boundary between success and annihilation. They are the most beautiful path toward the stars, and perhaps the most haunting. And as humanity considers this shimmering escape route, a final question flickers like a reflection on a sail. If we launch ourselves outward on beams of light, will we be chasing a future, or fleeing the shadows of our own limitations? The answer glows at the edge of the void, waiting for the sails to unfurl. It starts with a terrifying truth. Every dream of escaping the solar system, no matter how elegant or ambitious, collapses in the face of one brutal requirement: power. Not ordinary power, not the kind that lights cities or fuels rockets, but power on a scale that mocks our entire civilization. The energy needed to push a spacecraft beyond the sun's gravitational embrace for decades, centuries, or even longer is so immense that Earth's most advanced technologies look like flickering candles beside a raging inferno. Before humanity can even think about reaching another star, we must confront the staggering reality that our current energy capabilities are nowhere near enough. The cosmos demands strength far beyond what we currently possess. Picture Earth at night. The continents sparkle with city lights, shimmering like constellations scattered across the planet's surface. Highways gleam, towers glow, and the grid hums with electricity. It feels powerful, like we have harnessed energy on a grand scale. But zoom out. Look at Earth from space. Those lights fade into insignificance, tiny pinpricks against the overwhelming radiance of the sun. In a single second, the sun emits more energy than humanity has produced in its entire history. Our mightiest power plants, our largest reactors, our most complex grids, all of them combined are nothing more than a faint echo compared to the star that binds us. This is the heart of the power problem. Escaping the solar system requires propulsion systems capable of running continuously for years. It requires energy levels high enough to accelerate massive starships to incredible speeds, while also powering life support, communication, shielding, maintenance, and artificial gravity. And because we cannot refuel in the emptiness of interstellar space, every joule must be carried or captured. The energy demand grows into something monstrous, a tidal wave of requirement that crushes every traditional method. Chemical fuels are useless. Solar panels weaken as distance increases. Nuclear reactions help, but even they strain under the scale required for interstellar escape. Imagine a starship designed for such a journey. Its engines need to burn for decades, pushing relentlessly against the sun's pull. Its reactor must run flawlessly, generating power without interruption. Its shields must hold back radiation and micrometeoroids. Inside, entire ecosystems must be sustained, water purified, oxygen produced, food grown, waste recycled. Every circuit, every system, every mechanism needs energy. And the deeper the ship travels, the more energy is required to maintain stability and communication. The ship becomes a moving city, and a city cannot survive on whispers of power. Solar energy, humanity's most abundant resource, becomes useless beyond a certain point. At Jupiter's orbit, sunlight is already 96% weaker than on Earth. At Saturn, it fades into a dim glow. By the time a ship reaches the Kuiper Belt, the sun is little more than a bright star, far too distant to offer meaningful power. Solar panels that work beautifully near Earth become dead weight in deep space. A starship relying on solar energy is like a desert traveler carrying a bottle of melting ice. Eventually, there is nothing left to drink. Fusion power offers hope, but fusion itself remains elusive. Even if humanity achieves stable fusion reactors on Earth, building one compact, durable, and safe enough for a spacecraft is an entirely different challenge. Fusion demands magnetic fields, exotic materials, and precise control, all vulnerable to the chaos of interstellar space. A malfunction in deep space isn't an inconvenience. It's a death sentence. And even a perfect fusion engine requires enormous amounts of fuel, helium-3, deuterium, or other rare isotopes that must be painstakingly mined from moons or gas giants. The ship becomes dependent on resources scattered across the solar system, making the preparation for escape a monumental undertaking. Antimatter propulsion offers even greater power, but it introduces a nightmare of its own. Antimatter is the most energetic substance known. It annihilates everything it touches, releasing pure energy. Just a few grams contain enough power to launch a starship. But antimatter is rare, dangerous, and nearly impossible to store. Containers must use magnetic fields to trap it without letting it touch physical matter. If the field collapses for even a millisecond, the antimatter detonates with the force of a nuclear bomb. The starship becomes both a vessel and a ticking weapon, carrying within it the seeds of its own destruction. Even if we solve the propulsion problem, another challenge looms: communication. Sending signals across vast distances requires powerful transmitters and energy-hungry systems. A ship that travels far from the sun must carry its own power for communication, or risk falling silent forever. In the loneliness of interstellar space, silence is not peaceful, it is fatal. Without communication, the ship loses guidance, support, updates, and the ability to send data home. It becomes a ghost drifting between stars. And then comes the final, brutal realization: the power problem is not just a technical issue. It is a philosophical one. Even if humanity builds engines strong enough to escape, reactors stable enough to endure, and systems efficient enough to survive, we must ask ourselves whether we have the wisdom to wield such power responsibly. Great power has shaped human history for better and worse, splitting atoms, lighting cities, fueling wars, and transforming societies. Interstellar propulsion would be the most powerful force humanity has ever controlled. It could unite us under a shared destiny, or become a source of conflict, destruction, or imbalance. The cliff-edge contrast becomes clear. Our dreams require power beyond imagination, yet our civilization struggles to manage the power we already possess. We hold electricity in our grids, fire in our engines, and nuclear energy in our reactors. But the energy of the stars, the power required for interstellar flight, demands not just engineering breakthroughs but societal maturity. The universe waits, indifferent but patient. Somewhere out there, beyond the quiet sweep of the planets, lies freedom, if we can gather the power to reach it. But the next question rises, sharp as a blade cutting through darkness. Even if we harness such power, will it be enough? Or will the sun's gravitational grip remain unbroken, holding us here until we learn to command forces worthy of escaping its ancient dominion? The answer hides in the silence between stars, waiting for the day when humanity discovers whether it can rise to meet the cosmic power required to break free. They begin as sketches, circles around a star, lattices of light, impossible rings spanning millions of kilometers. At first glance, these megastructures seem like fantasies carved from science fiction. Yet the deeper humanity travels into the idea of escaping the solar system, the more these colossal visions transform from fiction into necessity. Artificial suns, Dyson swarms, stellar engines. These are not decorative monuments to ambition. They are the raw infrastructure required to command the power of a star. If the power problem threatens to cage humanity forever, then megastructures become our attempt to seize the key. To step beyond the solar system, we may have to reshape the sun itself. Imagine standing on a platform orbiting Mercury, the star filling half the sky, an overwhelming white-hot sphere whose surface rides with explosive storms. Now imagine thousands, then millions of such platforms drifting around it, each a mirror, a panel, or a collector built to capture fragments of this unimaginable energy. A Dyson swarm is not a single structure, but a massive collection of solar collectors orbiting in a synchronized ballet, forming a shimmering sphere of power. From a distance, the swarm would look like a luminous halo encircling the sun, a celestial crown forged by human hands. Its purpose? To harvest energy on a scale orders of magnitude beyond anything Earth could ever generate. And this energy is not for comfort. It is not for lighting cities or powering industries. It is for propulsion. For starships. For breaking the chains of the solar cage. Each mirror, drone, and collector in the swarm contributes a piece of the colossal energy budget needed to drive lasers, fusion reactors, or even light sails across interstellar distances. Humanity would become a stellar-scale civilization, the kind philosophers once whispered about only in theoretical hierarchies. A species that no longer merely inhabits a solar system but engineers it. Yet the beauty of these structures hides a vast, chilling risk. To build a Dyson swarm, humanity must tear apart planets, mining them not for resources but for their entire mass. Mercury could be laser-cut into dust and reassembled into mirrors and satellites. Asteroids would be harvested until they vanished. The inner solar system would transform from a natural landscape into a gigantic construction site. Engineers and machines would work for centuries, maybe millennia, assembling a system so large that even the sun would seem small by comparison. The cost is staggering, not just in energy but in the irreversible transformation of our cosmic neighborhood. Then there are the stellar engines, machines designed to move the sun itself. Yes, move it. A Shkadov thruster, for instance, uses a giant reflective structure to create asymmetric radiation pressure, nudging the sun slowly through the galaxy. Over millions of years, such an engine could reposition our entire solar system, steering it away from danger or toward unexplored regions. The idea feels mythic, like giving the star a rudder. But the implications are profound. If humanity can move the sun, then the solar system itself becomes a vessel, a cosmic arc shifting through the Milky Way. But this idea comes with its own terrifying contrast. A stellar engine is not a safe machine. If misaligned, if destabilized, if struck by a rogue object or sabotaged, it could unleash catastrophic forces. Imagine a thruster malfunctioning and redirecting the sun's radiation chaotically. Imagine the orbit of Earth being altered, the climate destabilized, the gravitational balance between planets disrupted. We would be tampering with forces so immense that mistakes could echo through millions of lives. The same machine capable of saving humanity could also destroy it. And then there is the psychological weight of this ambition. A Dyson swarm or stellar engine is not built in a decade or a century. It spans generations, civilizations. The people who begin the project will never see it completed. Their descendants may forget why it was begun. Entire nations could rise and fall while the construction continues silently in the vacuum. Megastructures require more than engineering. They require cultural endurance, unbroken purpose, and a shared vision powerful enough to bind humanity across ages. Imagine the view from within a finished Dyson swarm. The sun no longer shines freely across the planets. Instead, its light is broken into beams, redirected, harvested, shaped. The sky above Earth would glow with shifting geometries, panels glinting like metallic stars, lasers stretching like cosmic spears through the void. It would be beautiful, alien, unsettling. A reminder that humanity has rewritten the solar system to serve a single purpose: escape. But another haunting question grows beneath this achievement. If we build megastructures to capture the sun's power, will they imprison us even more tightly? A civilization dependent on stellar engineering might fear dismantling or altering these systems. The energy they provide, once essential for escape, could become essential for survival. Instead of freeing humanity from the solar cage, we might build a larger, brighter cage around ourselves, one made of our own creation. The contrast is sharp. Megastructures are humanity at its most visionary and humanity at its most vulnerable. They require wisdom equal to their power. They demand unity equal to their scale. They force us to confront a future where the solar system becomes both a masterpiece and a warning. As we ponder these colossal structures, one final thought flickers like a spark in the darkness. If alien civilizations exist, would we recognize their megastructures scattered across distant stars? And if so, are they beacons of progress, or tombstones of civilizations that sought escape and failed? The answer may lie in the shadows of our own artificial suns, in the gigantic machines we have yet to build, waiting for the day when humanity decides whether such power is our path to freedom, or our greatest and most dangerous temptation. It begins with darkness, vast, unbroken, absolute. A silence so deep it feels ancient, swallowing sound, light, and certainty in equal measure. Yet within that darkness, the planets move with flawless precision, each one tracing its invisible path around the sun. To escape this immense celestial machinery, humanity must learn to use its movements to our advantage. Gravitational assists, slingshots, are our way of borrowing momentum from worlds far larger than ourselves. They are the cosmic equivalent of grabbing onto a giant's arm and letting its strength hurl us forward. But this technique, elegant as it is, takes us into territory where mathematics becomes survival and where a single miscalculation can doom a mission forever. Imagine a lone spacecraft drifting toward Jupiter, its engines silent, its fate hanging on a trajectory calculated with near-religious precision. The planet grows larger in its windows each hour, a swirling, striped titan wrapped in storms the size of continents. But the ship does not intend to land. It intends to fall, deliberately, into the giant's gravity well. As it plunges inward, speed builds, the ship pulled faster and faster by Jupiter's immense mass. Then, at the perfect moment, it veers away, using the momentum it has stolen to sling itself outward at blistering velocity. No fuel consumed. No engine required. Just pure physics at work, a dance with gravity that transforms a world into a catapult. This maneuver is breathtakingly beautiful but also terrifying. The margins for error are thin as starlight. If the ship approaches too close, it risks being captured by Jupiter's gravity and trapped in endless orbit. Too far, and the slingshot fails, sending the craft drifting weakly into the void. Tilt even slightly off course, and the ship may plunge into the planet's crushing atmosphere, where pressure rises like a monstrous fist ready to obliterate everything in seconds. A gravitational assist is not simply a maneuver, it is a razor's edge disguised as a trajectory. Yet for all its risks, the slingshot is one of humanity's most powerful tools for escaping the solar system. Using the momentum of planets, spacecraft gain speeds they could never achieve with onboard engines alone. Voyager 1 and Voyager 2 owe their entire interstellar journey to a series of carefully orchestrated gravitational assists, a cosmic billiards game played across billions of kilometers. Without these slingshots, they would still be drifting somewhere near Jupiter, the solar wind slowly pushing against their fragile antennas. Picture the solar system as a vast, silent pinball machine, planets acting as massive bumpers. A spacecraft is the pinball, tiny in comparison, but capable of achieving extraordinary speeds if it hits those bumpers at exactly the right angle. But unlike pinball, there are no second chances. The paths must be plotted decades in advance. One mistake means never reaching the outer planets, never crossing the heliopause, never tasting the thin, cold breath of interstellar space. The slingshot method is both an opportunity and a threat, a reminder that every attempt to escape the sun's reach comes at the mercy of forces far beyond human control. As a spacecraft leaps from one planet to another, the emotional tension grows. Each successful assist is a triumph, pushing the ship farther into the unknown. But each maneuver also increases its isolation. The sun shrinks behind it. The planets become small, distant marbles. Communication delays stretch from seconds to minutes, then hours. The gravitational assists that propelled it forward are now far behind, unreachable. The ship becomes a lone traveler hurled into darkness by giants it can never return to. The slingshots that once gave it strength now serve as reminders of the home it left behind. And yet, there is something undeniably poetic about this method. Gravity, once seen as a prison, becomes a tool. The same force that binds Earth to the sun becomes the key to flinging a spacecraft beyond that very system. The universe reveals a subtle hint. Not all prisons must be broken, some can be used. Gravity becomes an ally, a silent partner in humanity's quest for escape. But the deeper the ship travels, the more the dangers shift. Once past the gravitational reach of the major planets, there are no more assists to rely on. Nothing to steal momentum from. Nothing to borrow speed. Beyond the Kuiper Belt, gravity fades into a whisper. The spacecraft is on its own, coasting with the final burst of momentum gifted by the planets. From here onward, only the energy it gained through those slingshots will carry it toward the distant stars. The silence grows colder. The darkness grows thicker. And the journey becomes a test of endurance rather than maneuvering. This transition, from being pushed by giants to drifting alone, mirrors humanity's own emotional experience with cosmic escape. The slingshots give us hope, momentum, and direction. But ultimately, they deliver us to a place where we must confront the unknown without guidance. The solar system can help us begin the escape, but it cannot carry us across the finish line. We must face the void on our own terms. Still, the gravitational assist remains one of the most elegant tools ever discovered. Humans did not invent it, they uncovered it like a secret written into the fabric of space. It is proof that even in the cold logic of physics, there is room for ingenuity, for creativity, for cosmic partnership. The planets themselves become stepping stones, guardians offering their strength to travelers daring enough to approach. But one haunting question remains: what if the slingshots are not enough? What if no matter how perfectly we navigate, no matter how precisely we borrow momentum, the final speeds we reach are still too small to break the sun's deepest gravitational chains? Will humanity forever linger in the outskirts of our stellar home, propelled by giants yet never free from their pull? The answer lies in the silence after the final assist, in the narrow transition between planetary control and true interstellar drift. It is there, in that fragile moment, that humanity must decide whether gravitational shortcuts alone are enough, or whether we must invent something far greater to take us the rest of the way into the eternal dark. It starts with a whisper, a quiet question that has haunted humanity since we first looked at the stars. If the universe is so vast, so ancient, so full of potential worlds, why don't we see anyone else? This is the heart of the Fermi paradox, a mystery as cold and deep as interstellar space itself. And when we ask whether humanity can ever escape the solar system, this paradox becomes impossible to ignore. Maybe we don't see anyone out there because leaving one's home star is far harder than we imagine. Maybe every civilization before us reached the same barrier we are now approaching, and stopped, trapped by physics, distance, power, or fate. Imagine drifting alone beyond Neptune, far from the warmth of the sun. The stars appear brighter here, sharper, like cold needles piercing the dark. In a place so quiet, so empty, the absence of alien footprints feels louder than any sound. Humanity has sent probes into this darkness. We have scanned thousands of stars, listened for signals, searched for patterns in radiation, looked for strange dimming of distant suns that might indicate megastructures. But what we've found again and again is silence. A silence so absolute it feels deliberate. And this silence raises a chilling possibility. Maybe we are alone because no one else has managed to escape their solar system either. The Fermi paradox holds a cruel mirror to our ambition. On one side, it fuels hope, suggesting that humanity might be the first, the pioneers, the brave spark in a quiet universe. On the other side, it whispers something darker, that perhaps interstellar travel isn't just difficult, it might be nearly impossible. Or worse, deadly. The paradox forces us to consider that the universe does not guarantee survival to those who reach for the stars. Maybe civilizations destroy themselves before they ever build ships. Maybe they exhaust their resources, choke their environments, or tear their societies apart. Or perhaps they reach for technology so powerful that a single mistake ends their story forever. But the darkest possibility is the great filter. The idea that at some point between the origin of life and the rise of starfaring civilizations, there exists a near impossible barrier. A barrier so severe that only a tiny fraction of species, if any, ever manage to pass it. The question then becomes terrifying: is the great filter behind us, or ahead of us? If it lies in our past, humanity is a miracle. If it lies in our future, then our attempt to escape the solar system might lead us directly toward it. Now imagine an ancient alien civilization on a distant world. Perhaps they built rockets, colonies, cities that glittered beneath alien suns. Perhaps they stood at the edge of their own solar system and dreamed of escape just as we do. Did they launch probes? Did they build megastructures? Did they experiment with fusion, antimatter, or starlight sails? And if so, where are they now? The emptiness between the stars becomes a graveyard of unanswered questions. The silence suggests that if they tried to escape, they failed, or never dared. It is in this cosmic quiet that philosophy and science collide. Perhaps intelligent life burns out quickly, unable to survive its own power or folly. Perhaps civilizations become inward-looking, retreating into virtual worlds, simulations, or digital utopias, abandoning physical expansion entirely. Perhaps the universe is filled with species that chose safety over exploration, fearing the dangers lurking in interstellar space. Or perhaps something else waits out there, something that keeps civilizations silent, hidden, afraid. The paradox never confirms, only provokes. This mystery strikes at the core of our own identity. Humans are explorers by nature. We crossed oceans, climbed mountains, split atoms, and mapped the invisible. The thought that we might reach a cosmic boundary we cannot cross is almost unbearable. Yet the Fermi paradox forces us to consider whether our desire to travel beyond the solar system is unique, or shared by countless species whose stories ended in darkness. It forces us to confront the possibility that the silence is not accidental, but a sign of the universe's harshness. But there is beauty in the paradox too. The silence may not signify danger. It may signify opportunity. If no one else escaped their star, then humanity might be the first species in the history of the galaxy to attempt it. The loneliness becomes empowering. The void becomes a canvas. The absence of alien megastructures around distant stars could mean that no one before us has reached that level of mastery, leaving the frontier open, waiting for footprints we have yet to make. Picture humanity's first true interstellar vessel leaving the solar system. Behind it, the sun glows like a brilliant lantern suspended in a cosmic ocean. Ahead lies endless darkness, sprinkled with distant stars, each one a possibility, a question, a test. The ship carries not just people or machines, but the weight of a paradox millions of years old. As the craft drifts farther from home, the silence around it becomes almost spiritual. It is the silence of possibility, of destiny, of a universe waiting to see whether humanity will become its first great wanderer, or another quiet absence. For all its uncertainty, the Fermi paradox serves a powerful role in our story. It forces us to confront the stakes. If we fail to escape our solar system, we join the silence. If we succeed, we break it. The paradox becomes a challenge carved into the night sky, a riddle with no answer except the one we choose to create. And so a final haunting question emerges, echoing across the darkness. If the universe is truly silent, then are we alone, or simply the first voice preparing to speak? The answer lies not in the stars but in our ability to reach them. They sit on the edge of the solar system like frozen secrets. Europa, Enceladus, Titan, worlds sculpted from ice and shadow hiding oceans, energy and mysteries beneath their frozen skin. These moons are nothing like Earth. Their landscapes are alien, silent and unsettling, shaped not by sunlight but by tidal forces, geological cracks and ancient chemicals drifting through their atmospheres. Yet despite their eerie beauty, these places may hold the key to humanity's escape from the solar system. Not because they are destinations but because they are launch pads, cosmic stepping stones where gravity is weaker, fuel is cheaper, and the dream of interstellar travel becomes a little more possible. Imagine standing on Europa. The sky is black even at midday, sprinkled with distant stars that gleam like icy needles. Jupiter fills half the horizon, a swirling giant whose storms tower taller than mountains. Beneath your feet, the ground is a crust of fractured ice, ridges and cracks stretching endlessly, hiding an ocean deeper than Earth's. The silence is absolute, broken only by the distant creaking of shifting ice plates. It feels like walking on the surface of a living ghost, a place both breathtaking and merciless. But Europa's beauty hides an advantage. Its gravity is barely 13% of Earth's. Launching a spacecraft from this frozen moon would require a fraction of the energy needed to escape Earth's pull. Now picture Enceladus. It is smaller, smoother, colder. A bright white marble drifting around Saturn. Geysers erupt from its south pole, shooting plumes of water and organic compounds hundreds of kilometers into space. A spacecraft could glide through these plumes and collect material without ever landing, harvesting resources directly from the moon's core. Its low gravity, just 1% of Earth's, makes it one of the easiest launch spots in the solar system. It is a world where the cost of escape shrinks dramatically, where even small rockets could achieve what monstrous engines require on Earth. And then there is Titan, Saturn's golden moon, cloaked in thick orange haze. Here, methane rains from the sky, lakes ripple under alien winds, and the atmosphere is so dense you could strap wings to your arms and fly. Titan is colder than death, but strangely welcoming in one critical way. Its air is thick, its gravity gentle, and its combination of conditions makes launching spacecraft easier than on any other major body in the solar system. A launch from Titan feels like a slow-motion ballet, rockets rising gracefully instead of exploding upward in violence and fire. Titan provides lift where Earth provides resistance. But these icy moons offer more than just easy launch conditions. They offer fuel. Europa and Enceladus hold oceans rich in hydrogen and oxygen, the ingredients for rocket fuel. Titan's atmosphere is full of methane and hydrocarbons, a celestial reservoir of chemical energy. Instead of dragging thousands of tons of fuel from Earth, humanity could mine the outer moons, convert their ice and gas into propellant, and turn their distant surfaces into cosmic refueling stations. The moons become not just launch pads but gateways. Yet beneath this hopeful vision lies an emotional tension as cold and sharp as their frozen landscapes. These moons are inhospitable, deadly, alien, unsettling. A human standing unprotected on Europa would collapse in seconds, lungs freezing, blood boiling, radiation tearing through their cells. On Titan the cold could shatter metal. On Enceladus, the vacuum would empty your breath before you even realized you were dying. These places test not just technology but psychology. They are reminders that humanity does not belong here. We are intruders in worlds that were never meant to hold life from Earth. Living on these moons would require sealed habitats, radiation shielding, heat sources, and constant vigilance. Machinery would freeze, fracture, or clog with ice crystals. Astronauts would feel the crushing loneliness of a world where no plant grows, no wind whispers familiar sounds, and the horizon is a barren line of frozen desolation. Titan's orange haze might feel claustrophobic, Europa's endless cracks like a shattered dream, Enceladus's geysers like warnings from below. These moons give with one hand and take with the other, offering fuel and launch potential, but demanding psychological resilience beyond anything humans have ever endured. Yet this contrast, between opportunity and danger, makes them vitally important. To escape the solar system, humanity must leave behind comfort, familiarity, and the gentle embrace of Earth. These icy moons force us to confront the reality that interstellar travel will not begin from paradise. It will begin from isolation, hardship, and sacrifice. The first true starships may not rise from Cape Canaveral or Baikonur, but from frozen plains beneath Jupiter's shadow, or methane-slick lakes beneath Saturn's rings. Imagine a future where humanity has outposts on these moons, small glowing domes against dark ice. Engineers work in pressurized suits, harvesting fuel from subsurface oceans. Robots glide across frozen terrain, mapping cracks and valleys. Above them, the first interstellar ship waits in orbit, refueled and ready. The sun is now a distant lantern, not a dominant tyrant. From these distant worlds, escape becomes not only possible but inevitable. But a haunting question lingers beneath the hope. If these moons are the stepping stones out of the solar system, what will humanity become once we build our new homes on such desolate shores? Will we remain earthlings in spirit, or evolve into something shaped by ice, distance, and endless dark? The answer may lie on these frozen worlds, silent, waiting, offering both the tools of escape and the price of achieving it. They say space is not a place, it is an enemy. A silent, patient adversary that attacks not with claws or teeth, but with emptiness, radiation, and time. For all our machines, our rockets, and our ambition, the greatest barrier to escaping the solar system may not be physics or power, but the human body itself. We are creatures shaped by Earth, by its gravity, its atmosphere, its magnetic shield, its cycles of light and dark. Remove these things and the body begins to unravel. To ask whether humanity can journey beyond the solar system is also to ask whether we can survive long enough to make that journey at all. Imagine floating in deep space, far beyond Earth's protective atmosphere. Radiation streams toward you like invisible arrows, charged particles from the sun, cosmic rays from distant galaxies, bursts of energy from ancient supernovae. Earth shields us from nearly all of it, wrapping our bodies in a cocoon of magnetic fields and atmosphere. But in space that protection vanishes. Every second, radiation tears through cells, damaging DNA, disrupting tissues, igniting mutations. Astronauts on the International Space Station face increased cancer risks after a few months. A journey to Mars pushes the limits of safe exposure. A journey beyond the solar system, lasting decades or centuries, becomes something far more dangerous. Without breakthrough shielding, a human body would slowly burn from the inside. Then there is microgravity, gentle, almost peaceful at first glance. Astronauts float with ease, drifting through spacecraft like dancers in slow motion. But the body was not built for floating. Within days, muscles begin to weaken. Bones become brittle, losing density as though aging decades in mere months. The heart reshapes itself, blood pools in strange places, vision clouds, immune systems weaken. Microgravity is a kind of silent disease, eroding the body piece by piece. For missions lasting a lifetime or more, microgravity would become a slow-motion unraveling of what makes us human. Artificial gravity could help, but generating it requires massive rotating structures, spinning habitats, or propulsion systems that create long-term acceleration. These technologies are complex, heavy, and untested on the scale required for centuries-long voyages. Yet without them, interstellar travel becomes a battle between human biology and the void, a battle the void will eventually win. But radiation and microgravity are only the beginning. Psychology becomes another battlefield. Imagine living in a confined vessel for decades, surrounded by the same faces, the same walls, the same recycled air. No trees, no oceans, no sky, no horizon, only corridors and screens. The mind, starved of sensory variety, begins to fray. Isolation breeds anxiety. Repetition breeds despair. Small conflicts become enormous. The ship becomes less a vessel and more a pressure cooker where emotion and stress build in claustrophobic cycles. Humans evolved in vast landscapes filled with unpredictable stimuli. A starship offers none of that. And then there is time. A journey beyond the solar system is measured not in weeks or months, but in years, decades, even generations. The people who begin the journey will not be the ones who finish it. Their children and grandchildren must inherit the mission. This continuity demands discipline, culture, and purpose, qualities that can erode under isolation. Imagine being born on a ship, knowing you will die on that ship, never having seen Earth, never having felt wind, never having walked under a sky. Would you still feel connected to the mission? Or would the ship become a prison whose original dream feels irrelevant? Biology itself becomes a question mark. Long-term exposure to radiation may alter reproduction. Changes in gravity and environment may affect development. Medicine we take for granted on Earth may fail in space. A small infection could become a deadly outbreak. A minor injury could become catastrophic. The further the ship travels, the harder it becomes to rely on Earth's assistance. Doctors must work with limited supplies, limited equipment, and no emergency evacuation. Every illness becomes a high-stakes puzzle. But the deepest biological challenge is evolution. Human bodies are tuned to Earth's environment. Remove that environment and evolution begins to drift. Muscles, bones, organs, all may adapt differently in a long-term space population. After centuries, the descendants of interstellar travelers may not even resemble Earth-born humans. They may be taller, lighter, with altered vision, bone structure, and tolerance to radiation. These changes could be subtle or dramatic. In escaping the solar system, we may slowly escape our own species. This possibility raises profound emotional and philosophical questions. What does it mean to be human if our biology changes? What happens when the children born in deep space feel no connection to Earth at all? Will they still consider themselves explorers? Will they feel like exiles? Will they want to continue the journey their ancestors started? The contrast becomes sharp and unsettling. The dream of leaving the solar system demands that we abandon the very biology that makes us who we are. To go forward, humanity may have to shed the limitations of flesh. Gene editing could strengthen bones, enhance radiation resistance, and stabilize hormones. Cybernetic implants could replace failing organs. Artificial wombs might ensure healthy births in hostile environments. Neural interfaces could compensate for sensory deprivation or psychological strain. Humanity may need to become post-human, not out of desire but out of survival. Yet this transformation raises its own fears. By altering ourselves to survive the journey, do we risk losing the essence of humanity? Does escaping the solar system mean becoming something new, something unrecognizable? And if so, is that a price we're willing to pay? The human body, for all its grace and resilience, was crafted by Earth. Every cell carries the memory of forests, oceans, sunlight, and gravity. Leaving the solar system means leaving behind the environment that shaped us. To survive that departure, we must evolve, not over millions of years but within a handful of generations. As we imagine humanity standing on the threshold of interstellar travel, one final question lingers like a heartbeat in the dark. Will we escape the solar system as humans, or become something else entirely by the time we break free? They say every great journey changes the traveler, but what if the journey to the stars changes us so completely that we cease to be human at all? When we imagine escaping the solar system, we picture metal ships, glowing engines, and the cold vacuum of space. But the deeper truth is far stranger. the key to reaching the stars may not lie in better rockets or stronger engines, but in reshaping humanity itself. The limits of biology, psychology, and mortality weigh heavily on every attempt to imagine interstellar travel. And so a new idea emerges, quiet at first, then revolutionary. If the human body cannot survive the journey, then perhaps the answer is to build something that can. Picture a lab glowing with the electric blue light of artificial intelligence systems. Rows of servers hum softly like mechanical hearts, each one running simulations of star systems, trajectories, and cosmic hazards. Engineers watch as AI-driven probes navigate models of interstellar space with perfect precision. These machines feel no fear, no fatigue, no loneliness. They do not need oxygen, food, water, or gravity. They can travel for centuries without complaint. In many ways, they are the perfect pioneers. If humanity cannot go to the stars, then perhaps our creations can go in our place. Imagine an AI craft built to endure the harshness of interstellar travel, armored against radiation, capable of repairing itself, guided by algorithms that learn and adapt. It could travel where humans cannot, dive into star systems too dangerous for fragile bodies, and send back knowledge that reshapes our understanding of the universe. But sending AI alone feels incomplete, almost hollow. We dream not only of seeing the stars but of touching them, living among them, claiming the darkness as part of our story. For that, AI is not enough. Humanity wants to carry something more than intelligence into the void. We want to carry our identity. And so the next idea emerges, one far stranger and more controversial: uploading the human mind. Imagine scanning every neuron, every memory, every emotion, and recreating it inside a digital vessel. A consciousness freed from flesh, capable of traveling across the stars encoded as information. Such a mind could be transmitted as data, carried on beams of light, or stored inside artificial bodies built to survive the cosmic cold. The physical limitations of biology, radiation, aging, disease, simply vanish. A digital human could drift through the galaxy for millennia, exploring worlds long after Earth itself has changed beyond recognition. But this vision carries a shadow. Is a digital copy truly you, or just a simulation wearing your memories? If your consciousness is recreated in a machine, is the original you still bound to die? Does the uploaded version have the same soul, the same identity, the same humanity? These questions echo through philosophy, psychology, and ethics, creating more uncertainty than answers. Uploading the mind might allow humanity to cross the stars, but at the cost of blurring the boundary between human and machine until the distinction collapses. Yet there is another path, one that alters not the mind but the body itself. Genetic engineering. Biotech. Evolution by design. Instead of abandoning biology, this approach rewrites it. Imagine humans with bones strengthened against microgravity, skin resistant to radiation, organs engineered for efficiency, immune systems reinforced to withstand cosmic threats. Children born for space. Bodies crafted to survive where Earth-born physiology fails. These post-human travelers would be our descendants, yet different, adapted to a life among the stars, shaped not by Earth's forests and oceans but by the metal corridors of starships and the distant glow of alien suns. Gene editing might produce individuals with enhanced longevity, allowing a single person to live long enough to see an interstellar voyage completed. Or it might produce humans capable of entering suspended animation without damage, slowing their bodies to a near stop for centuries. It might even produce forms that survive on minimal resources, or bodies resistant to the psychological stresses of isolation. The possibilities are as vast as they are unsettling. Then there are hybrid models, humans fused with machines. Cybernetic implants. Neural interfaces. Augmented senses designed to perceive radiation, gravitational waves, or cosmic patterns invisible to ordinary eyes. A person equipped with such enhancements would not merely survive the journey, they would experience the universe in ways no human ever has. Their senses would stretch across wavelengths. Their thoughts could interface directly with spacecraft systems. Their lifespans might expand dramatically with technological support. But whether through AI, digital consciousness, genetic engineering, or cybernetic augmentation, all these visions share one truth. To escape the solar system, humanity may have to let go of what it means to be fully human. The transformation may be subtle or radical, but it will be inevitable. The universe is not kind to fragile creatures of biology. It rewards resilience, adaptability, endurance. The travelers who cross interstellar distances may be heirs of our species, but they will not be identical to us. They cannot be. This raises a haunting question. If humanity evolves into something new to survive the journey, what becomes of the humanity we leave behind? Will Earth-born people and star-born people drift apart culturally, psychologically, biologically? Will future generations view their planet-bound ancestors with nostalgia, or with indifference? And then comes a deeper fear. What if the beings who finally escape the solar system look back on Earth the way adults look at childhood homes, fondly but with no desire to return? The contrast becomes sharp, almost painful. Our dream of escaping the solar system is rooted in human longing, yet the path requires becoming something beyond human. This tension defines the future, the desire to explore meeting the cost of transformation. As we picture the first post-human starfarers drifting into interstellar darkness, one final question pulses like a heartbeat in the void. Will humanity's greatest voyage be a triumph of survival, or the moment we evolve beyond everything we once were? Disaster has always been one of humanity's greatest teachers. Fire taught us to gather. Storms taught us to build. Famine taught us to innovate. And every catastrophe, no matter how devastating, has pushed humanity to evolve, to rethink, to transcend. When we ask whether humanity will ever escape the solar system, we often imagine curiosity leading the way, scientific ambition, exploration, wonder. But history whispers a darker truth. Progress is rarely born from comfort. It is born from crisis. Catastrophe may not just motivate our escape, it may force it. The future of interstellar travel might begin not with triumph, but with desperation. Imagine Earth in the distant future. The sky grows darker as volcanic ash spreads from a supereruption. Entire continents tremble beneath tectonic fury. The oceans churn with storms that dwarf anything in our history. In the chaos, humanity looks upward, not for hope but for survival. A supervolcano like Yellowstone could launch billions of tons of ash into the sky, blotting out sunlight for years, collapsing ecosystems, disrupting agriculture and plunging civilization into a grinding struggle for life. Earth, our cradle, would suddenly become a threat. And in the face of that threat, the idea of escaping the solar system would transform from fantasy to necessity. Then consider asteroid impacts, ancient killers that reshaped worlds long before humanity existed. The dinosaurs never saw it coming. A 6-mile-wide rock tore through the sky, igniting global fires, triggering tsunamis, sending shockwaves across the planet. Humanity, for all our technology, remains vulnerable to the same cosmic bullets. A large enough asteroid could erase cities in a heartbeat, scorch continents, or plunge Earth into a nuclear winter. Even if humanity survived, civilization might not. In the shadow of such destruction, we would be forced to consider a future that no longer depends on a single planet. We would need colonies, ships, refuges, lifeboats waiting beyond Earth's sky. And then there is the sun itself. A star is a living thing, restless, temperamental, capable of violence on unimaginable scales. Solar flares and coronal mass ejections hurl billions of tons of charged particles into space. Most of the time, Earth's magnetic field shields us. But a sufficiently powerful eruption could overwhelm our defenses. Power grids fried. Satellites disabled. Communication networks crippled. In minutes, the modern world could fall into a silence broken only by fear. And this is only the beginning. In a billion years, the sun will brighten enough to boil Earth's oceans. In several billion, it will swell into a red giant, consuming the inner planets. The clock is ticking, even if we pretend not to hear it. Imagine the world watching a solar storm unfolding in real time. The skies shimmer with violent auroras stretching across entire continents. Satellites drop from orbit like dying birds. Power grids fail. The planet trembles under electromagnetic fire. In that moment, humanity would understand just how fragile our civilization truly is. The solar system is not a sanctuary. It is a battlefield of cosmic forces indifferent to life. Escaping may one day be the only way to preserve our existence. But catastrophe is not always external. Sometimes the danger comes from within. Human conflict, warfare, environmental collapse, engineered pandemics, any of these could push civilization to a breaking point. In a world where nations fight over dwindling resources, the dream of interstellar travel may shift from noble exploration to an act of survival. A ship leaving the solar system could become a seed, preserving culture, knowledge, and genetic legacy in case Earth falls into ruin. Picture a future where rising seas consume coastlines. Cities drown beneath relentless storms. Crops fail as climates shift faster than societies can adapt. In such a world, technology becomes a race against extinction. Starships become lifeboats, built not out of ambition but out of fear. The emotional tone shifts from wonder to urgency. Every bolt, every circuit, every test flight becomes part of a desperate attempt to outrun collapse. The journey to the stars becomes a choice between transformation and annihilation. Yet catastrophe does more than threaten, it inspires. It forces humanity to look beyond old boundaries. After every crisis in history, humanity has emerged stronger, smarter, more united. A global threat could ignite a kind of unity never before seen. Nations might combine resources, scientists might share knowledge freely, and humanity might finally see itself not as divided tribes but as a single species struggling against a hostile universe. The fear that drives us could also be the fire that unites us. Imagine the first interstellar ship built not by one nation, but by all of humanity working together. A ship forged in the aftermath of disaster, designed to ensure our future. Its launch becomes a moment of collective rebirth. Billions watch as the engines ignite, carrying their hopes into the void. Behind them, Earth is wounded but alive. Ahead lies uncertainty, danger, challenge, but also possibility. This contrast, catastrophe and hope, defines the emotional heart of Section 17. Catastrophe is the shadow, but hope is the light that breaks through it. In every moment of fear, humanity finds the spark of courage. In every disaster, we find innovation. In every threat, we find determination. And as we look toward the stars, that determination becomes a question pulsing with urgency. Will catastrophe be the force that finally pushes humanity to escape the solar system? Or will we wait too long, trapped by our own hesitation until disaster closes the window forever? The universe does not promise survival. It does not promise safety. It offers only opportunity and danger. The choice in the end is ours. Disaster has always been one of humanity's greatest teachers. Fire taught us to gather. Storms taught us to build. Famine taught us to innovate. And every catastrophe, no matter how devastating, has pushed humanity to evolve, to rethink, to transcend. When we ask whether humanity will ever escape the solar system, we often imagine curiosity leading the way, scientific ambition, exploration, wonder. But history whispers a darker truth. Progress is rarely born from comfort. It is born from crisis. Catastrophe may not just motivate our escape, it may force it. The future of interstellar travel might begin not with triumph, but with desperation. Imagine Earth in the distant future. The sky grows darker as volcanic ash spreads from a supereruption. Entire continents tremble beneath tectonic fury. The oceans churn with storms that dwarf anything in our history. In the chaos, humanity looks upward, not for hope but for survival. A supervolcano like Yellowstone could launch billions of tons of ash into the sky, blotting out sunlight for years, collapsing ecosystems, disrupting agriculture and plunging civilization into a grinding struggle for life. Earth, our cradle, would suddenly become a threat. And in the face of that threat, the idea of escaping the solar system would transform from fantasy to necessity. Then consider asteroid impacts, ancient killers that reshaped worlds long before humanity existed. The dinosaurs never saw it coming. A 6-mile-wide rock tore through the sky, igniting global fires, triggering tsunamis, sending shockwaves across the planet. Humanity, for all our technology, remains vulnerable to the same cosmic bullets. A large enough asteroid could erase cities in a heartbeat, scorch continents, or plunge Earth into a nuclear winter. Even if humanity survived, civilization might not. In the shadow of such destruction, we would be forced to consider a future that no longer depends on a single planet. We would need colonies, ships, refuges, lifeboats waiting beyond Earth's sky. And then there is the sun itself. A star is a living thing, restless, temperamental, capable of violence on unimaginable scales. Solar flares and coronal mass ejections hurl billions of tons of charged particles into space. Most of the time, Earth's magnetic field shields us. But a sufficiently powerful eruption could overwhelm our defenses. Power grids fried. Satellites disabled. Communication networks crippled. In minutes, the modern world could fall into a silence broken only by fear. And this is only the beginning. In a billion years, the sun will brighten enough to boil Earth's oceans. In several billion, it will swell into a red giant, consuming the inner planets. The clock is ticking, even if we pretend not to hear it. Imagine the world watching a solar storm unfolding in real time. The skies shimmer with violent auroras stretching across entire continents. Satellites drop from orbit like dying birds. Power grids fail. The planet trembles under electromagnetic fire. In that moment, humanity would understand just how fragile our civilization truly is. The solar system is not a sanctuary. It is a battlefield of cosmic forces indifferent to life. Escaping may one day be the only way to preserve our existence. But catastrophe is not always external. Sometimes the danger comes from within. Human conflict, warfare, environmental collapse, engineered pandemics, any of these could push civilization to a breaking point. In a world where nations fight over dwindling resources, the dream of interstellar travel may shift from noble exploration to an act of survival. A ship leaving the solar system could become a seed, preserving culture, knowledge, and genetic legacy in case Earth falls into ruin. Picture a future where rising seas consume coastlines. Cities drown beneath relentless storms. Crops fail as climates shift faster than societies can adapt. In such a world, technology becomes a race against extinction. Starships become lifeboats, built not out of ambition but out of fear. The emotional tone shifts from wonder to urgency. Every bolt, every circuit, every test flight becomes part of a desperate attempt to outrun collapse. The journey to the stars becomes a choice between transformation and annihilation. Yet catastrophe does more than threaten, it inspires. It forces humanity to look beyond old boundaries. After every crisis in history, humanity has emerged stronger, smarter, more united. A global threat could ignite a kind of unity never before seen. Nations might combine resources, scientists might share knowledge freely, and humanity might finally see itself not as divided tribes but as a single species struggling against a hostile universe. The fear that drives us could also be the fire that unites us. Imagine the first interstellar ship built not by one nation, but by all of humanity working together. A ship forged in the aftermath of disaster, designed to ensure our future. Its launch becomes a moment of collective rebirth. Billions watch as the engines ignite, carrying their hopes into the void. Behind them, Earth is wounded but alive. Ahead lies uncertainty, danger, challenge, but also possibility. This contrast, catastrophe and hope, defines the emotional heart of Section 17. Catastrophe is the shadow, but hope is the light that breaks through it. In every moment of fear, humanity finds the spark of courage. In every disaster we find innovation. In every threat we find determination. And as we look toward the stars, that determination becomes a question pulsing with urgency. Will catastrophe be the force that finally pushes humanity to escape the solar system? Or will we wait too long, trapped by our own hesitation until disaster closes the window forever? The universe does not promise survival. It does not promise safety. It offers only opportunity and danger. The choice in the end is ours. They will remember the moment for generations, not because it was loud but because it was quiet. Humanity's greatest triumph did not arrive with fireworks or roaring engines or a flag planted in alien soil. It arrived in a moment of stillness, the kind of silence so vast it feels holy. After centuries of dreaming, building, sacrificing, and evolving, humanity finally touches the stars, not with tentative curiosity, but with the full weight of a species ready to claim its place in the cosmos. Section 19 is the culmination of everything, the emotional, philosophical, and cinematic climax of the entire journey. It is not just the end of the story, it is the beginning of a new one. Imagine the crew standing in the observation deck of their interstellar ship. The hull is quiet now. The fusion engines have powered down. The sails are fully unfurled, shimmering like ghostly wings as they catch the faint pressure of distant starlight. The ship drifts through interstellar space with grace, momentum carrying it like a leaf floating on an endless cosmic river. The sun, once a massive tyrant dominating the sky, has dwindled into a single point of light, tiny, pale, yet shining with the emotional weight of everything the crew left behind. It is no longer a star that rules them. It is a memory. Ahead, a new star glows, Proxima Centauri, dimmer and smaller than the sun, but radiant in its promise. Around it, the faint silhouette of a possible planet glitters like a secret waiting to be discovered. The crew watches in awe as this new world grows brighter, its details sharpening with each passing day. They have crossed a boundary no human has ever crossed. They are witnessing a sight no eye born on Earth has ever seen, the light of another sun shining through the observation window. The emotional contrast strikes them with staggering force. Behind them lies the entire history of humanity, millions of years of evolution, countless civilizations rising and falling, wars and peace, art and science, hopes and fears. Ahead of them lies a blank page in the cosmic story. A place where no map exists. A place where no footprints have ever been laid. A place untouched by humanity's struggles or triumphs. In that brief, shimmering pause between two suns, the crew realizes something profound. This is not the end of humanity's story. It is the moment we truly become a cosmic species. Inside the ship, their lives have been shaped by decades of preparation, sacrifice, and change. They are not the same humans who once looked up at the night sky from Earth. Their bodies have adapted. Their minds have expanded. Their technology is integrated into their biology. And yet, despite all this transformation, something ancient still lives within them. The spark that pushed their ancestors to cross oceans, climb mountains, and wonder what lay beyond the horizon. That spark burns brighter now than ever before. The ship's log records their first transmission as they approach the new system. It is not a message of conquest or dominance. It is a message of gratitude for the journey, for the civilization that built the ship, for the people who dreamed of possibilities beyond Earth, and for the vast, indifferent universe that allowed their fragile craft to survive the crossing. The words echo through the corridors like a hymn. We are the children of the sun, and today we greet another. The approach becomes a cinematic transformation. The new star brightens, its light bathing the ship in a soft, unfamiliar glow. Shadows form in colors they've never seen before. Instruments hum with new readings. The planet ahead reveals oceans, continents, clouds swirling in alien patterns. Life may or may not exist there, but possibility itself is enough. The crew feels a mixture of awe, fear, hope, and humility. They are the ambassadors of a species that dared to leave its cradle, stepping into a universe that owes them nothing. The emotional weight becomes almost overwhelming. For the first time, humanity is not defined by Earth. The solar system is no longer the boundary of our story. A new chapter begins, not written by myth or imagination, but by the footsteps of human descendants touching alien soil. They imagine the moment the ship's landing craft descends through the thin upper atmosphere of this new world. The engines hum softly. The sky shifts into colors unseen by human eyes. A new horizon rises, sharp, foreign, inviting. When the landing craft touches down, the dust swirls around the hull in slow, silent spirals. The door opens. A figure emerges. Their boots press into alien ground, leaving the first imprint of humanity beyond the solar system. There is no crowd. No anthem. No celebration. Only the crisp whisper of distant winds, the subtle hum of unfamiliar life beneath the soil, and the quiet realization that the universe is suddenly a little less lonely. The moment is profound not because it is loud but because it is reverent. A single footprint becomes the symbol of everything humanity endured. The wars avoided, the catastrophes survived, the technologies built, the fears conquered, the bodies adapted, the minds expanded. For the first time, humans are no longer a planetary species or even a solar species. They are interstellar. And as the figure looks up at the alien sky, at the distant gleam of the sun, tiny and faint, a final thought settles over them like cosmic dawn. We left our cradle not to flee, not to conquer, but to grow. The future stretches out before them, vast and limitless. Other stars. Other worlds. Other discoveries waiting in silence. The journey has only just begun. And somewhere in that endless expanse the universe whispers back, welcome. It begins with a feeling, quiet, heavy, indescribable. A feeling humanity has never known before. Not the thrill of launch, nor the terror of danger, nor the awe of discovery, but something deeper, something ancient. It is the moment after the triumph, when the dust settles, the cheers fade, and the universe reveals the truth that has been waiting in its silence. Escaping the solar system is not an ending. It is an awakening. Section 20 is the epilogue, the reflection, the echo of everything humanity has endured. It is the moment when our species stands between what we were and what we are about to become. Imagine centuries after the first successful interstellar mission. No longer is there one lonely vessel drifting between the stars. There are several, some crewed by humans, others by post-human descendants, others by AI explorers carrying echoes of human memory. Each one follows a different trajectory through the galaxies. Some toward promising exoplanets. Some toward mysterious signals. Some simply wandering, mapping the cosmic coastline of the Milky Way. The solar system, once the entirety of human existence, is now just a point of origin, like an ancestral village remembered in stories. Yet Earth remains. Blue, fragile, beautiful. Still home to billions. Still turning quietly beneath a luminous sun. People walk its forests, swim in its oceans, climb its mountains. And every person alive carries a truth written into their bones. Humanity is no longer bound to one star. The solar system is no longer a cage. It is a birthplace, a memory, a chapter. Children now grow up learning that humans live under many suns. They study the sky knowing their cousins may be standing beneath completely different constellations. Humanity has dispersed, not in chaos but in harmony. Now imagine a monumental gathering. A cosmic anniversary. Across star systems, across habitats, across planets both familiar and alien, humans and posthumans and digital minds connect through a network stretching light-years. Holographic gatherings shimmer in orbiting stations. Voices echo across the void, translated, synchronized, merged into a tapestry of connection. They are celebrating the centuries since the first vessel crossed the heliopause, the moment humanity became interstellar. A message plays across every corner of the human expanse. A recording from the archives of the first starship. The raw voices of explorers who left the solar system with trembling determination. Their words sound simple now, almost fragile. We take this step for everyone yet to be born. And as those words echo across worlds, quiet tears fall. Because the promise was kept. But this moment is not just sentimental. It is philosophical. Every generation asks, what does it mean to be human now? On Proxima b, humans with genetically enhanced bone structures till alien soil that Earthborn bodies could never endure. On a free-floating starship, digital minds maintain poetry archives spanning centuries, their consciousnesses woven through quantum processors. On Titan, methane-adapted humans glide through thick orange skies, their lungs reinforced to breathe a hybrid mix of oxygen and inert gases. On Earth, traditional humans, unaltered, unchanged, walk under a familiar blue sky, preserving the oldest version of humanity as a living cultural treasure. Are they still one species? Are they still one people? The answer comes not through biology but through choice. They choose to remain connected. They choose to share knowledge. They choose to call each other family across light years. Humanity has not fractured, it has expanded. This realization marks the true escape from the solar system. Not the moment the first starship crossed the heliopause, not the moment the first human touched alien soil, but the moment humanity embraced its own diversity as strength. The solar system produced one kind of human. The galaxy produced many. And yet they remain bound together by a single ancient thread, the desire to understand the universe and themselves. Now imagine looking at the Milky Way from the surface of a distant world, one with violet skies and twin moons. The galaxy arcs overhead in a shimmering river of stars. Somewhere within that glowing band lies the sun, too far away to see with the naked eye. Yet the traveler knows it is there, shining quietly, warming Earth, anchoring memories. And for the first time they understand something profound. We are no longer children of the sun. We are children of the galaxy. The ships that once struggled to break free from the solar system now glide between stars as naturally as ancient sailors crossed oceans. The dreams of scientists, philosophers, artists, and explorers have merged into a shared legacy. Humanity has become a civilization of starfarers, restless, curious, unafraid. And in the quiet moments, beneath alien constellations, a realization settles like cosmic dust. The question was never, will humanity ever escape the solar system? The real question was, what will humanity become once it does? The answer unfolds across countless worlds, countless forms, countless minds, yet all share the same origin, the same spark, the same story that began on a blue planet orbiting a yellow star. The solar system gave us life. The stars gave us purpose. And the journey continues, endlessly, beautifully, across the greatest canvas ever known.